All right, welcome everyone. Today we're talking about arc length. So this is back from chapter 8, although we've kind of held off on it. I think last Friday I told you that we actually get three different arc length equations. And so we kind of put them all together more or less. We're going to get arc length in Cartesian coordinates, and that's what this is here. You get arc length with parametric equations or parametrized curves, and that's going to be in 10.2. And then we get arc length for polar curves, and that's going to be, I believe, one of the topics in 10.4, although we do a lot of area as well. So yeah, we'll see three different types of arc length equations. And the big thing is like if you have a Cartesian equation, you should use the Cartesian arc length. If you have a parametrized curve, you should use that arc length equation. If you have a polar curve, and so it's very kind of telltale signs, I guess, is when you use what equation. Just depends on what kind of equation you're presented. And so this is dealing with the Cartesian stuff. I guess before we get into going through the video and doing a quick review of what you should have taken away from this before coming to class, are there any questions or things kind of in general, I guess? Maybe I could say a few just quick administrative announcements, right? The lab practicum is tomorrow. That opens, well, it's available starting at like midnight tonight or something like this. You have all Tuesday and Wednesday to do this. There is no pre-lab that goes along with this. Hopefully you've been reading Dr. Willie Wong's emails, the course supervisor. Been very kind of good about laying out all the pieces, but I know they sometimes get kind of long. So yeah, no pre-lab stuff. It's all going to be just kind of on D2L. It's multiple choice. Last I spoke with him, they were still whittling down a few questions. They have kind of too many, and they're taking a few out here, but they're aiming for 15 to 20 questions. So it's not going to be monstrously long or anything like this. And you have a long time, right? You have all of Tuesday and all of Wednesday in order to do this. And it's supposed to be a reflection on the past labs that you've done. And again, they're multiple choice in D2L, so you'll get your score kind of immediately once you have this submitted. I think that's really the only administrative thing. Of course, make sure you're doing all of your web work homework and things like this. But I'll pause here if there are any questions or things that I'm missing or forgetting about. I see there's a few questions. What's popping up here, Alec?
So yeah, I encountered a problem on 10.3 assessment that web work didn't accept as a decimal that was very close to the correct answer. Has there been any thought of expanding the amount of answers that are correct? Yeah, usually does not like decimal answers.
Yeah, I would say that's, so yeah, it doesn't like decimal answers except for in 10.3 where the goal is literally to sketch the curves. And so in that case, it was, I remember this is a few semesters ago, it was very, very tight. And then they opened up the tolerance on this a little bit. I'm not sure, I haven't really heard about, really recently this semester, for instance, about expanding that even more, but it's possible, I guess. Anything else?
Let's see, once we start the practicum, will there be a time limit to finish it?
No, so this is kind of like the other lab assignments in D2L, where kind of you have a big window so you can open it up. You can look at all of the questions, write them all down if you'd like, or print them, or whatever you'd like to do. And then just kind of exit that page, go back. You can look at kind of the post-lab videos that are, again, linked on that nice long email. And so, yeah, you kind of have a long time to do this. So take your time with it. Essentially, the way I'm viewing it is that these are free points. That if you put in the time and the effort, I think everyone could achieve, a very good score on this, certainly 95 or higher percent. And so, yeah, just take your time, give it some effort, and I think that everyone should be doing quite well on this. So the big thing, though, someone pointed out in one of the previous labs, right, that once you hit that submit button, right, you only get one submit. And so I kind of have to, there's a little bit of a game that you can play here. I mean, you can kind of wait until the last minute sort of deal, or that once you're happy with all of your answers, because you can't change them after you submit that. But also you don't want to forget either, right? So if you wait too long and then you forget to submit, that could also be very bad. So If you are going to, wait until the last minute, I would set some phone alarms, and I usually recommend to my students, right, that you set alarms on 2 different devices because always one seems to die, right? So yeah, anyway, especially, usually this comes up for like the final exam or things like this, right? That oversleeping can be quite monstrous. So yeah, if you're going to set some alarms and play this sort of game, I would set 2 different alarms on 2 different devices. Yeah, anything else?
Let's see. One of them I just typed out an answer to, and then there's one more here. Will the multiple choice questions for the lab be similar to the pre-lab questions?
Well, the pre-lab questions are really serving a different purpose, right? At least, especially with the in-class labs, right? They were really checking to make sure that you looked at the code ahead of time, that you thought about it, and that you're coming to class prepared, basically being a good group member. The lab practicum is more of a reflection exercise. And so I don't think that they'll necessarily be similar. I mean, they are both multiple choice. So in that regard, yes, right? They'll be similar in that. But I think the style of question will maybe be a little bit more substantive with the lab practicum. Okay, well, with that, why don't we go ahead and start into the 8.1 stuff here. So again, we're talking about arc length in Cartesian coordinates, and we're going to get a bunch of these arc length equations. But this is really the meat of the section right here. So this very first box of how to compute the arc length, and then kind of we'll apply this arc length formula to lots of different situations, right? Lots of different examples. But this is really the meat of it right here. And so you can do this with respect to x, or you can do it with respect to y. Essentially, just exchange your x's for y's, and the claim is that it works out fine. And this is very similar to when we were integrating between curves or things like this. We can integrate with respect to x, we can integrate with respect to y. Both seem to work out just fine. The big thing here that I want you to recognize is that we have a square root 1 plus some stuff here, and square roots in general are quite nasty things, right? This is kind of the lead or the build up to trigonometric substitution, is how do you deal with square roots in general. And so we'll see that there's really only a handful of problems, and I'm kind of going to take us through all the different types of problems more or less that are reasonable, that don't require trigonometric substitution, right? The ones, I mean, certainly we could. Trigonometric substitution is a part of this class, and so, I mean, we could ask that. I mean, maybe that would make a decent final exam question, but those become very long problems, remember. And so, by and large, we kind of stick away from those and do it, kind of a few of these kind of tricks where maybe the square root goes away, right? Maybe you have a perfect square under there, or things like this, or maybe some nice U-substitution. So we'll see those kind of flavor of problems quite a lot in today's class. So for instance, here's one right here where we found the arc length for this curve. And notice that once we go ahead and we take the derivative, when you square it, and we get to this point here, we can get a common denominator. And we happen to see that this thing right here, oops, why didn't my pen go off? There we go. This part right here happens to be a perfect square, right? Certainly the denominator is a perfect square, and you can see that very quickly. The numerator, it takes a little bit more time, right, to see that this is actually a perfect square, that this is just x to the 4th plus 4 quantity squared. And so then the square root takes out that squaring, and then the integral becomes much more reasonable, right? And so quite often we'll see things like that where they are perfect squares. This is kind of a tough one jumping into it. Maybe we'll do a few nicer ones and then get to this level in today's class. Okay, I think that's really all I wanted to cover. Of course, we do a few more examples here in the video, but this is really, again, the meat of what I wanted you to take away from the class videos, the pre-class videos. Any questions or things that we should be talking about, Alec?
I don't think so. I always kind of mentioned that, these integrals tend to be very easy to set up. A lot of times they are hard to calculate, and you have to sort of get lucky with something like that perfect square falling out. And so the problems can seem a little bit contrived, but you can always set the integral up, and there's all kinds of online, as soon as you have a definite integral, any graphing calculator will even do the integration for you. So it's a very practical thing to have, even though sometimes algebraically they you have to get a little lucky.
Yes, yes. There's, I guess, without having calculators and whatnot, a lot of these problems can seem very contrived. I agree with that. All right.
We have a question here. Is there any other equations for 8.1, or is it all arc lengths?
Nope, just all arc length.
That's the arc.
You can scroll through this. I mean, this talks a little bit about the proof of why the arc length formula works. This one's a little bit a funny thing here, where kind of you hold off on saying what the ending point is, the terminal point, and you just make that a variable. And this is called an arc length function. Actually, in Math 234, if you're continuing on and you take Math 234, you'll actually see a three-dimensional equivalent of arc length. So you'll get another arc length formula. And there are some good reasons why maybe kind of leaving that endpoint as a variable that you can plug in later is quite useful. But basically, this is, again, just arc length. And then, again, you see kind of some more examples. But, yeah, it's just really that one equation, more or less. Sometimes you use y's instead of x's. Sometimes you kind of think about your terminal point as a variable itself, so that way you can specify it later. But yeah, this is it. It's a relatively nice section, I think, all things considered. Okay, so with that, why don't we go ahead and start in on some of our new problems for today. Find the exact length of the curve given by y equals 6x to the 3/2 power on the interval from 0 to 1, right? So you can imagine, you can sketch this sort of deal, and it looks like, you know, some interesting curve here. And we want to know how long exactly is that curve. So that's the question of arc length. And again, we're going to use our formula here. So arc length formula goes, well, in this case, we have a y equals, right, in terms of x's, and we're specifying that x ranges from 0 to 1. And so it's going to be most natural if we go ahead and use the x version of the arc length equation. And we're going to integrate from x equals 0 to x equals 1 with respect to x. And now the arc length formula says we need to take the square root of, and you always have 1 plus, and then you need the derivative of your equation squared. So, okay, well, we need to do a little bit of work to take the derivative of our equation really quick. So let's go over here. So 6x to the 3/2. And if we take the derivative of this, well, the 3/2 comes down. And let's see, I think we're going to have, what, 9x to the 1/2 power, right? Because the 6 and the half would cancel a little bit, but there's a 3 there. Yeah, 3 times 3 is 9. Good. Reduce our power by 1, so it goes from x to the 3/2 to x to the 1/2. Okay, this is looking good. This is our derivative. This is what we go ahead and plug in here. So yeah, this was y and y prime. Just good to form these good habits, you know, when you're taking exams and stuff like that, showing your work and exactly what each one of these things is. Okay, and now we need to go ahead and evaluate this integral. So this is a relatively nice one because, right, this x has a square root in it. So when we square this, this is just going to become x. Don't forget to square that 9, though. That's probably the most common mistake that I see for a problem like this, that you forget to square the 9. And so this is a relatively nice setup. This is just a nice U-substitution. So like I said, we were starting off with kind of even an easier one than what we did in the videos. And so we can do a U equals 1 plus 81x. And du is going to be equal to 81 dx. So if you'd like to, you can make this dx is equal to du divided by 81. And so instead of dx, let's go ahead and write du divided by 81. And now this is just root u. There's a couple of different ways that you can go about this. I'm going to temporarily think about, right, and this is just the same with all u substitutions, right? You can either change these bounds and make these, you know, u values here, or you can kind of temporarily think of it as an indefinite integral, right? Find the antiderivative, and then swap back in for x's and plug in your original x values, right? So that's the way that I'm going to do. I'm going to kind of temporarily think about the indefinite integral here. Remember, the square root is the same thing as just raising to the 1/2 power. And so when we integrate this, this is the power rule in reverse, right? We go ahead and we up our power by 1. And then we go ahead and multiply by the reciprocal of our new power here, so 2/3. Let's not forget about this 1/81 that's hanging out over here. And so let's see, let's now go ahead and swap back in everywhere we see u's. Let's put our x's, right? So u is equal to 1 plus 81x. Let's see, this 81 and this 3, that's going to be what, 243, I believe. So 1 plus 81x instead of our u. This is being raised to the 3/2 power. So that's all of the work for the antiderivative, right? So now we need to go ahead and plug in our specific starting at any point, 0 to 1. So let's go ahead. If we plug in 0 into this, you have to be careful because quite often, I guess I should plug in 1, and then I'll get to that. So if I plug in 1, we're going to have 2 over 243, and then let's see, 1. So 1 plus 81 is going to be 82 raised to the 3/2 power, minus, and then this is what I was getting to, right? So quite often when you plug in 0 into these integrals, you get out 0. And so quite often, right, we just kind of forget about this. But in this case, right, when you actually plug in 0, this 1 kind of saves it to some extent, right? You don't just get 0 out across the board. You get 1, well, raised to the 3/2 power. Well, 1 raised to any power is just going to be 1. And then we have to multiply that by the 2 over 243. So this is really this 2 over 243 times 1, right, when we plug in this 0. So this right here would be my final answer. This is the exact length. There's really nothing, it'd be nice if we could simplify down this 82 raised to the 3/2 power, but there's really no way to simplify it beyond this. And so this is what I would enter into WebWork or on quizzes, exams, anything like this. Any questions, things that you'd like to add, Alec?
No, I would just say, as Ryan already mentioned, you could also just change the limits on the integral. So if you did that, when you have u as 1 plus 81x, then the 0 on the bottom would turn into a 1, and on top it would become an 82. So that's the other way you can do it.
Yep, and that's represented well in our final answer too, by the way. So if you like this method, right, so when x is equal to 0, plug that into your transfer equation here. This has the equivalent of u equals 1. When, x is equal to 1, our upper bound, and you plug that in, you get u is equal to 82. There we go, right? And so you could just make this here from 1 to 82, right? And then now those are u values, so you're plugging them in for u. And notice in our final answer, we have an 82 and we have a 1, right? So that's the other way to go about this. Also works quite well. All right, here's another one, getting a little bit more challenging here. Notice instead of having raised to the 3/2 power, we now have being raised to the 2/3 power. Also, I have an x equals, right? And we have y's here. So we're just going to use the other form of the arc length equation. The other form of the arc length equation, right? Basically just interchange the x's and the y's here. So we're integrating from y equals 1 to y equals 8. Again, we're integrating with respect to y here. And then we need to take the square root of 1 plus the derivative squared. And this time when we take the derivative, it's going to be the derivative of our equation, but with respect to y. So, okay, we take the derivative here. So again, we have 3/2 y to the 2/3 plus 4. And when we take the derivative of it, this 3/2 and the 2/3 perfectly cancel out, right? And so you're left with y. Well, we have to reduce our power by 1. So this is going to be y to the negative 1/3. And when you take the derivative of 4, well, that's just 0. I speak. So plus 0. Yeah, derivative of 4 is 0. There we go. And so let's go ahead and plug this in here. So y to the negative 1/3. That's our derivative. Now let's go ahead and evaluate this. So again, the setup's kind of done. You'll see some WebWork problems, by the way, where you just have to do the setup, right? You don't have to actually evaluate. So it's possible that you'll see some places where you just plug in this answer. Some of them we can evaluate, but again, by hand, there's only really a few that you can really do by hand. Otherwise, you get into kind of the trig sub and stuff like this. All right, so this is going to be y to the negative 2/3 power here. And so we need to think about this. This doesn't look very perfect squarey or anything like this. So let's maybe go ahead and try to do a rewrite here and see if we can't get anything to happen with this. So maybe the first thing that I'm going to go ahead and do is turn it into a fraction, right? Because we have this negative exponent here. So we can make this 1 over y to the 2/3 power. And then let's go ahead and get, right, we now have kind of two terms being added together. Let's get a common denominator and see if that does anything for us. So let's see, y raised to the 2/3, I need to multiply that here and on top and on bottom here. So we're going to have y to the 2/3 plus 1 divided by y to the 2/3. And okay, the top, that doesn't look like anything that's a perfect square that would cancel out with a square root, but at least the bottom does, right? Because we have this, remember the 2/3, this is being squared here. There's two actions happening, right? You're taking the cube root and you're squaring this thing. And so with this, well, the square root will at least cancel with that squaring down there. So again, the numerator, I'm going to leave this alone. Sadly, you can't distribute these square roots across addition. Otherwise, life would be quite grand here, I suppose. But we get something like this. So again, I've applied my square root to just the denominator here. I've split up that square root. You can split up square roots across multiplication and division. So that's why we were able to do that, but sadly not the addition or subtraction. Okay, so the claim is we have made some progress, but it may be hard to see exactly what to do next. So right, you can kind of sit around and think about this, but the question is, right, is there a natural U-substitution? That's kind of a fruitful way to go here. And so, well, usually with U-substitution, we let it be the inside function. So I guess if we were to try a U-substitution, you know, letting U be equal to this y to the 2/3 plus 1, that's inside of the square root still. That we couldn't break free. And so maybe that as a U-substitution would be reasonable. So with this, let's go ahead and take the derivative to calculate out du. So we're going to have 2/3 and y to the negative 1/3 dy. And this is very important, right? This is the first place where you can see that this is actually a fruitful idea, that this is a good way to go, because these pieces right here are represented in our integral, right? Y to the negative 1/3, that's the same thing as dividing by y to the 1/3. So we see those pieces, the du actually appears here, and so that's going to be very good. Let's go ahead and move forward then. I'm going to rearrange this a little bit. I'm going to write, what, 3/2, so I'm bringing the 2/3 over. I'm going to bring this y to the 1/3 over, and this is all with our du, and this is what is equivalent to dy. Right, so again, I brought the 2/3 over by multiplying by 3/2, the reciprocal. I've multiplied by y to the 1/3 on both sides, and that cancels it out on the right-hand side, and then dy. Okay, so now let's go ahead and I'm going to do the U substitution. So again, temporarily I'll think about this as an indefinite integral. This is going to be root U, and I still have this y to the 1/3 in the bottom. And instead of dy, I'm going to write 3/2, y to the 1/3, and du. And you can see again, right, the way that you know that U substitution is working well is if, right, you're successfully able to transfer over all of your y's into u's, right, or all of your x's, whatever your other variable was, into u's. So now we're just integrating essentially the square root of u again, right? And so we can go ahead, in fact, why don't we go ahead and practice this other method for fun here. Let's go ahead, I want to transfer this into a definite integral with respect to u. Since I did the last one in this indefinite method, let's go ahead and just transform this over. And so I need to take my y value of 1 and my y value of 8, right? Those are my upper and lower bounds. So y equals 1, y equals 8. We're going to plug those into our exchange equation and see what is the equivalent u for these things, right? So if I plug in 1, well, let's see, 1 to the 2/3 is going to be 1, plus an extra is going to be 2 altogether. If I plug in 8, well, again, there's kind of two things that's happening, right? We have to square it and we have to take the cube root. Well, if we square it first, right, that's going to get quite large. So I'm going to go ahead and take the cube root first. The cube root of 8 is nice, right? The cube root of 8 is just 2. And so if we square that, we're going to get 4 plus the 1. So altogether we get 5. So this is going to be integrating from 2 to 5. If we go ahead and we swap this out, instead of y values, we just do u values. And so let's go ahead and factor out this 3/2. Let's integrate. So again, the square root of u, that's the same thing as raised to the 1/2 power. So when we integrate, we're going to need to raise our power by 1. So from 1/2, it goes to 3/2. And we need to multiply by our reciprocal here of our new power. So instead of 3/2, right, it's 2/3. That's the reciprocal. And you can see actually everything cancels out very nicely, right? The 2's, the 3's nicely cancel out. And now since we transform these into u values, right, we don't need to swap back for y's. Right? And we can just plug in u equals 2 and u equals 5. And that's kind of why this method is sometimes quite nice. And so if I plug in 5, I'm going to have 5 to the 3/2. If I plug in 2, I'm going to have 2 to the 3/2. And this right here is my final answer. Again, for these arc length equations, your answer should always be a positive number, right? We're asking how long is a curve. And so you should always be getting a positive answer. If you get an answer that's 0 or negative, this is a point of concern. A good time to kind of pause and go back and see what went wrong here. So this is something you can see that just changing again from this 3/2 power to a 2/3 power here. This took us down a very different rabbit hole, right? Where we kind of, again, it was a U-substitution, but we had to do some algebra before that. And then even then, right, we weren't maybe as confident about the U-substitution that we were making. We were like, well, it's something to try, right? Usually U-substitution with the chapter 7 techniques is the first thing that we should be thinking about. And it happened to work out. But again, kind of it's a lot less obvious than the first one. So this is kind of a more moderate or difficult problem even. Questions or things you'd like to add, Alec?
Nothing to add. We had a question here. Could you do a trig sub? Could you let u equal y to the, well, they have negative 1/3. I think you'd probably want to try y to the positive 1/3 and look at a tangent, see what would happen.
Oh, trig sub. Yeah, we don't usually do trig subs so much when you have these rational exponents, right? The fact that this is raised to the 2/3 power, I'm not ruling it out because I know there's sometimes these kind of very surprising ways that you can solve these problems, and that quite often there are multiple ways to go about these things.
Yeah, if you did a u sub first and you had u as y to the 1/3, then you'd have a u squared plus 1. I suppose at that point you could do a tangent, but you would have already done a u sub, and then the trig sub just makes it harder than it needs to be, I think.
Yeah, I don't see a natural way of doing that. But again, I'm very reluctant to say no, it won't work, because I've been surprised, you know,
yeah,
especially like with grading exams and stuff like this. There's like, it's like, oh yeah, I didn't know it could be done that way. But you know, the student finds the correct answer and does it, you know, kind of in a surprising way. Okay, so let's go ahead and move on. Find the length of this curve on the interval from 1 to 2. So in this case, we have a y equals sort of deal. And this right kind of looks somewhat similar anyway to the one that you saw in the video. So the one that we kind of went over. So maybe we're expecting a similar sort of trick here. So let me go ahead and maybe pause and give you 90 seconds or so. I'll go ahead and start writing out at least the beginnings of a solution. So if you'd like to, you can peek up and you can see what I'm working on. But I'm not going to talk to you for 2 minutes or so, and I'm going to let you work, and then we'll kind of go over our results together. So if you can, please ignore the screen for the time being and work on this problem on your own. Or if you're watching this, you know, after this class, pause the video here, right? Work on this on your own, and then we'll go over the results together. another 30 seconds or so. All right, let me go ahead and start talking through what I was able to come up with. Of course, we can apply the arc length formula here. So I have my square root, my 1 plus, my derivative squared, and we're integrating this with respect to x from x equals 1 to x equals 2. Here, the derivative, it's okay if you took an extra line or two in order to do all these things and cancel. I just kind of wrote out the result and did probably too much in my head, admittedly. But remember that this is the same thing as x to the negative second power, right? So there's a negative 2 that comes down, there's a little bit of canceling, and then when you reduce your power, that becomes x to the negative third power. That's why I have x cubed in the denominator, right? Because it was a negative exponent, so I pushed it into the denominator here. So I took the derivative here, and hopefully you did it as well carefully, and then I went ahead and I plugged that into my equation. So that's what it kind of looks like. This was a binomial, and there's a couple of different ways that we can go about this, right? So in the video, I got a common denominator. I went about it this method, and I wanted to show you a slightly different method here. And so if you like the video method more, by all means, you can certainly use that. You can get this common denominator, and then you can go ahead and square the top and the bottom, and that works out perfectly fine. Then you add your 1, so on and so forth. I'm going to show you another method that I think it ends up being a little bit faster. There's a few more fractions, but I kind of want to show you this trick as well. And so for this one, right, I just kind of leave it as is, and I decide I'm going to expand out just with it as is. And so I go ahead and write, whenever you have a binomial squared, you have to be very careful. I wrote out, and I need to have both of these, and I'll kind of explain why I wrote out both of these. But here we have, I guess it's more like this bottom one here. So you need to square the first bit, and then you minus, and you multiply them together, and you double it, right? It's minus 2ab, and then you add on b squared, right? And so essentially, I applied that formula here. And so that's what I came up with. So when I FOIL it all out, again, you don't have to use this trick that I wrote down in green there, right? You can just kind of actually multiply it by itself, and you do the first, the inners, the outers, and last, and you get to the exact same results, right, after simplifying. But I wanted to show you, when we go ahead and, right, we see this extra 1 out here. When we incorporate that 1, notice that it combines, and there's a like term with it, this negative 1/2. And remember, this negative 1/2 came from this bit right here, right, the minus 2ab. And so when we add in this plus 1, it essentially becomes very similar to what we started with, but now this is plus 1/2. Rather than minus 1/2. Otherwise, right, that's the only really like term here. And at this point, right, we can see basically that adding that 1 has just kind of changed the sign, right? Instead of negative 1/2, we now have plus 1/2. And the claim is that this actually itself is a perfect square. And so that's why I wrote out this other one here, is that notice that if you were to change that middle term from a negative to a positive, right, that this is also a perfect square, and it's just a plus b quantity squared. So again, if you like the video method more, right, where you kind of get lots of common denominators and all that sort of stuff, you can certainly use that. But I can say a little bit quicker, you know, using this method, that this is just going to be kind of essentially what I started with, right? But instead of that minus sign, there's going to be a plus sign there. I know that this is going to be x cubed minus 2 plus 1 over 2x cubed quantity squared inside of my square root here. And so this is kind of one that otherwise it's very difficult to see that this actually is a perfect square, right? So this is the same thing as what I have below it here, this thing quantity squared. right? But I think it's quite difficult to see that without kind of looking at it from this lens or sort of deal, kind of this viewpoint. So yes, this is a perfect square. Again, you can certainly use the video method, and kind of that perfect square is a little bit more straightforward. Let me just, I'm going to flip back to the video problem that I keep on referencing, just in case if anyone's lost and saying, wait, which one are you talking about? Right, so it's this first example that we did here, 8, 1, 3. Again, kind of, it's a very similar sort of deal. I just changed the exponents kind of slightly here. And notice, instead of leaving it like this, where we have these two separate fractions, right, we just got a common denominator and plugged that in. Right, and so that also works out fine, but you can see it took a few more steps, right? A few more steps, but it certainly works well. And FYI, right, notice that you started off with x squared over 4 minus 1 over x squared here, and the thing that you simplified down to was the exact same, but you just had a plus instead of the minus. And so that's exactly where we're headed as well. When we look at ours, in this case, we started off with, I clicked on the exact same one. Class, there we go. We started off with a minus, and now when these square roots and the squares cancel out, we have the integral from 1 to 2 of x cubed over 2 plus 1 over 2 x cubed. It's the exact same thing, but instead of the minus sign, we have a plus sign. Still need to integrate, can't forget about that. So yeah, and we just did this a little bit faster, I'd say. Now let's go ahead and integrate. So when we integrate this, right, raise our exponent by 1, divide by our new exponent. So when we divide by 4, that combines with 2 down there. And when we integrate this, let's see, well, I need to raise my exponent by 1. Let me take this a little bit more carefully here. So this is going to be x raised to the negative 2nd power, right? It goes from -3 to -2. And then I need to divide by my new exponent, right? So, okay, these would combine. And I have 1/4, it's negative. And if I wanted to, I could simplify, right, pushing this x down into the denominator here, or this x squared really down into the denominator here. Okay, now we need to evaluate this from 1 to 2, and we win the game. So if I plug in 2 here, well, 2 raised to the 4th power is going to be 16. We need to divide that by 8, minus 1/4, and 2 squared is going to be a 4. So that's all when I was plugging in 2. When I plug in 1, I'm going to have 1/8 minus 1/4. I'm sure that there's a little bit of simplifying that I can do, but all of these denominators kind of look different, and I don't really want to spend too much time on this. So this right here, maybe I'd be tempted to just input this into WebWork as my final answer. Certainly if you have a little bit more time, right, you could get it all kind of one denominator. You'd have to have, what, 16ths. Any questions here? Okay, then. Well, then moving on, I like this problem here because it's kind of a good real world problem. I mean, so yeah, quite literally when you suspend a wire from two sides, right, you can wonder what kind of shape does this make, right? And it is actually this hyperbolic cosine. And so this is true. And we want to know what kind of length of wire, right? So, I mean, if you're actually out on the job, I suppose, well, you probably just bring more wire and don't risk it and bring the exact amount that you need. But the question is really, like, how much wire do you need in order to suspend it from these two towers here that are, looks like they're what, 40 feet apart, 40 meters apart or something like this. So meters, yeah. So, well, we have this equation, y equals 20, hyperbolic cosine of x over 20. And again, kind of we have these two towers, one's down here at x equals -20, one's over here at x is equal to 20. And we want to know how long is this wire? How long is this curve here? So that's the exact situation that we're studying today, arc length. And so, well, we need to do the integral from -20 to 20, the square root of 1 plus, and our derivative squared. This is all, you know, the function and everything is in terms of x's, so we're going to be integrating with respect to x and everything. Let's go ahead and take the derivative. So y prime, well, let's see, the 20 is along for the ride. When we take the derivative of hyperbolic cosine, it becomes positive hyperbolic sine. That's the big difference between regular sine and cosine and hyperbolic sine and cosine, right? Is that cos just goes to sinh here. Let's see, leave the inside alone. And then we multiply by the derivative of the inside. So the derivative of x over 20 is going to be 1/20th. So we can see there's a little bit of canceling that goes on here. And then this is hyperbolic sine of x over 20, I suppose. And so, okay, we have 1 plus hyperbolic sine, right? And again, right, we haven't really figured out, we haven't really done like trig sub or anything like this when we have hyperbolic sines on the inside. And so my question is, right, just like in this last one, we had that this bit right here was secretly actually a perfect square, right? That we could exchange this for some perfect square, and then that canceled with the square root. And I think something very similar is going to happen here, but the question is, what can I exchange this for? What perfect square is this equivalent to? So I'm going to pause for 30 seconds or so. If you know the answer, please type it out in chat for me. Or at least the idea here. What can I trade this in for? What perfect square is this equivalent to? Monday after Easter is quiet. I see it here. So yes, the big thing is that you can use this kind of one of the fundamental equations really with hyperbolic sine and hyperbolic cosine is that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. And so if you go ahead and rearrange this, right, we can see that hyperbolic cosine squared is the same thing as 1 plus hyperbolic sine squared. Oops, I forgot the h. So here we have 1 plus hyperbolic sine squared. And so we can go ahead and exchange this in for hyperbolic cosine squared. Oops, I forgot my u here. Probably Alex yelling at his screen saying, Ryan, no. So let's see, u in this case was x over 20. Hyperbolic sine squared, square root, and there we go. So now again, the square and the square root nicely cancel. And so we're left with just hyperbolic cosine of x over 20. Now there's no problem with integrating this, right? So this is really just a small u sub, but you can do kind of a guess and check sort of deal. It's going to be a lot like sinh, right? Hyperbolic sine of x over 20. Just right, if we were to check and if we were to take the derivative of this, right, the chain rule means that we need to multiply by 1/20th. So in order to counteract this, right, we're going to throw in a 20 here. So double check, right, to see that this is the correct antiderivative, because if we take the derivative of this, we get back to where we started, right? That's 1/20th and the 20 cancel out now. We need to evaluate from -20 to 20. And so when we do this, let's see, we're going to have what, hyperbolic sine of 1 minus and hyperbolic sine of -1. Oh man, I'm really tempted to kind of plug all these things in. I think it cancels even more, right? We can write hyperbolic sine in terms of e's and stuff like this, and I think it would cancel even more. But this is where I'm going to end it, right? After this, it's all just arithmetic. We've done all of our calculus, all of our knowledge about hyperbolic sines and cosines and everything. So this is what I would enter in for a quiz, for an exam, for homework. Questions? Comments? Concerns? Okay, moving on then. here's a problem where we won't see this one necessarily all the way through. We're going to set it up, we're going to simplify, and then I just end here with identify which method of integration. So this one turns out to be kind of quite long if we were to do it all the way out from start to finish. But then I think that this is a good one that we could set up, we can try to simplify, and then we're just going to identify, right, how would we finish this one up? So, okay, here's the function. Let's do this one together. So arc length is given by the integral. Looks like we have x's and they go from 0 to 1/2. We have the square root of and 1 plus, and we need the derivative and we're going to square it. So derivative quantity squared with respect to x. So that's what y is. Let's take the derivative here. The derivative of the natural log is going to be 1 over. Leave the inside alone. Then we need to multiply by the derivative of the inside. So the derivative of the inside is going to be negative 2x. And so let's see, we have negative 2x divided by 1 minus x squared. Let's go ahead. I guess we could technically leave it right like this. We have an integral that represents the length of the curve. Part B is simplify this definite integral so that we get it without any square roots. So I'm going to do just one more line here, do a little bit of simplifying since I know I need to simplify it. And then we're going to simplify it even more in part B. So 0 to 1/2, the square root of 1 plus, and let's go ahead and square these things. So we have, well, this is going to be 4x squared in the numerator here. And then in the denominator, I'm trying to think, do I really want to square this all out? Let me go ahead and just leave this as 1 minus x quantity squared here. Oops, sorry, this is 1 minus x squared. I'm not going to expand this bit out. We'll see that actually we want it in this form, right? Because we're going to get a common denominator, and I'm hoping that the square root here is going to cancel with this squared here, right? So that's my hope. So that's why I'm thinking that I want to leave it maybe like this. Let's see, maybe I'll decide against it here in a few steps, but right now that's how I'm feeling anyway. All right, so let's go ahead and get a common denominator here, so that way we can actually start distributing this square root and hopefully seeing things cancel out. So 0 to 1/2, and we're going to go ahead and multiply this 1 by 1 minus x squared squared on top and on bottom. Right, so now this is just a fancy representation of 1. We're adding to that our 4x squared divided by 1 minus x squared quantity squared. And so if you'd like to, you can even skip this step a little bit and just kind of put them all over 1, right? This common denominator that we were aiming for here. And it would look something like this, right? So now that we have this common denominator, you can even kind of cheat using technology here and just kind of center that a little bit. That looks a lot nicer. And then we could go ahead and distribute the square root. So distributing the square root, in the bottom here, notice that it's going to cancel out with a square. And that's exactly what I was hoping we'd be able to get to. So this denominator is just going to be 1 minus x squared, right? Because the square root and the squared canceled there. Now in the numerator, I see a lot of things squared, but it's not all being squared, right? That darn plus sign here in the middle, there's no really way to distribute the square root across that plus sign, right? And so we need to do a little bit of work here. And this is a place where kind of very similar to that first problem we did in the pre-class video. I think by expanding out the square here, hopefully we can see that this quantity on top is actually a perfect square as well. Remember, our goal here is that we're just going to try to get this so that we don't see any square roots. We're going to simplify until there's no more square roots. So that's how we know we're done. So, okay, let's go ahead. If I was to expand this out, right, and I'm going to FOIL this out here, doing the first, the inners, the outers, the last, all that sort of stuff. Let's see, I'm going to have, right now I'm just kind of looking at my copy up here. Let's see, the first, when I do this, I'm going to have 1. The inners and the outers, right, I'm going to have minus x squared and minus x squared. And when I do the last, I'm going to have plus x to the 4th. And so, okay, we could simplify. And this would be minus 2x squared. And now I see this trick is happening very similar to what we did earlier today, right? I see that there's a minus 2x squared and there's a plus 4x squared, right? So these like terms are going to combine, and we're going to go from negative 2x squared to positive 2x squared. So same sort of trick here. 1 minus x squared. And this is going to become the square root of 1 plus 2x squared plus x to the 4th. And so now we stare at this for a second, right, and say, okay, is this a perfect square? Is there any way to write this as some quantity squared? And the answer is yes, because again, kind of we see that this trick went from negative 2x squared to positive 2x squared. So this is just going to be kind of essentially what we started with, but instead of a minus sign, it's going to be a plus sign, right? So basically just swaps that. So this is going to be the integral from 0 to 1/2, the square root of 1 plus x squared quantity squared. And if certainly, right, if this was on one of the assessment sets, if this was a quiz, if this was an exam, I'd be a little bit paranoid, right? And I'd take this and I would expand it out, right? This would be my guess, my hypothesis, but I would expand it all out and I would verify that I get kind of what I started with. And so, but yeah, this is, I'll tell you, it is correct and everything, but it's good to be a little bit paranoid when it comes to quizzes and exams, right? And just make sure that things are working the way that you think that they're working. All right, so with this square and square root, now they finally cancel, and we're left with 1 plus x squared on top, 1 minus x squared on bottom, integrating with respect to x, and this is where B ends, right? I now have it written, no square roots needed. So this is what it's been able to be simplified down to. And then in part C, we're not actually going to do this all the way out, but we're just going to identify which method of integration would we use in order to do this. So I guess first off, we can eliminate U-Substitution won't work. Well, we got rid of the square root, so I'm not thinking trig sub. But I remember, right, there's one that deals specifically when we have polynomials over polynomials, which integration technique is used to take care of these rational functions, these polynomials over polynomials? Anyone remember from our chapter 7 days? Partial fractions. Partial fractions take care of polynomials over polynomials, aka rational functions. So partial fractions will be the answer to this. This one's a little bit even more annoying because the degree of the numerator is the same as the degree of the denominator. And when that happens, right, you need to use polynomial long division to take care of that first. So you'd use polynomial long division first to rewrite this in a better form. Then you would go ahead and use partial fractions in order to actually evaluate that resulting division and get your final answer. So this is why I don't want to do this in class, right? Is because this can take quite a long time. It's not really the focus of today's class, but it is another problem that kind of can be done. All the square roots go away. It is possible to do by hand. It takes some time. This is a long one. Any questions? Anything you'd like to add, Alec?
I think you got it covered pretty well. Looking for questions, not seeing any so far.
All right. Well, if you have any questions, go ahead and type them out or whatnot, or you can also raise your hand. I'm happy to call on folks if you don't mind speaking and stuff like this. But yeah, if you have any questions, go ahead and write them out and we can come back and answer them as well. So I have a couple more examples here. So you got about 5 minutes or so. Let's do at least, I think we can get through them all. It'll be a little bit tight, but we can run a few minutes over if need be. This is another one kind of, you see, we're probably going to be dealing with this trick with the exchanging between hyperbolic sines and hyperbolic cosines. This one does have an x equals and it's in terms of y, so just getting some practice viewing it from that perspective. But again, it's really not that bad. It's just interchange, instead of x's, just use the y values. And when we take the derivative with respect to y. And again, kind of it's all going to work out pretty much the same. And so when we take the derivative of this, let's see, well, the derivative of 2 is just 0. The derivative of hyperbolic cosine is hyperbolic sine. So let me go ahead. This is going to be x prime, I suppose, over here. So I have a 1/6. Derivative of hyperbolic cosine is hyperbolic sine. Leave the inside alone. Then we take the derivative of the inside. And the derivative of 6y, again, with respect to y, is just going to be 6. So you can see these kind of cancel out. Hyperbolic sine of 6y, quantity squared here. So again, remember from earlier, if you go ahead and rearrange that hyperbolic cosine minus hyperbolic sine is equal to 1, you see that you can exchange this for just hyperbolic cosine squared. And you just need to leave the insides the same, right? Whatever that is, just leave it the same. So in this case, it's 6y, so we leave it as 6y. This is a fruitful exchange because now you have just one thing squared inside of a square root. So that means that these things are going to nicely cancel. By the way, in the pre-class video, maybe I was a little bit more careful with this. But you can go back through all of these examples here. And I've always kind of, technically, I just haven't brought it up, or you could say I missed it, or made this as a mistake. But I was pretty intentful with it that, technically when you take the square and the square roots, they don't exactly cancel, right? You technically have this absolute value going on here. But if you go back and you see every single one of our problems on the interval that we're concerned with, so in this case, we're on the interval from 0 to 5 in particular, right? That hyperbolic cosine is always positive on this interval. And so if you're taking something that's already positive and you're throwing it inside of a square, you're throwing it inside of an absolute value, the absolute value is just not doing anything. And so that's why time after time, I just kind of drop it, right? In this case, hyperbolic cosine is always positive. So it doesn't really matter the interval from 0 to 5. But you have to be a little bit careful. So for instance, like these ones here, notice we did a lot of canceling with the square roots and the squares. And so technically these should be inside of absolute values here. But on the interval from 0 to 1/2, notice that they're always positive, right? So certainly the numerator is always positive, no matter what values you plug into it. But 1 minus x squared, that's not true, right? We have to really use the fact that we're on this interval from 0 to 1/2. If you tried to plug in something like 2 or 3 or something like this, right, that wouldn't be so true anymore. So, and this is, by the way, representative. This is not something, I'm like cheating you out of anything by doing this. I've never really seen a question on, quizzes, exams, homework, anything like this where that hasn't been the case. So for these sort of arc length questions, right, pretty much the thing that you're always getting is positive. All right, let's go ahead and integrate this. This is going to go to hyperbolic sine. And just like before, kind of we need, something for the chain rule to cancel out with. So this is going to be 1/6. We evaluate from 0 to 5. When you plug in 0 into hyperbolic sine, remember that's when we actually know the value of. It's just 0. And so we're going to get 1/6 times the hyperbolic sine of 30, right? So that's when we plug in the 5 there. And again, when you plug in 0 into hyperbolic sine, that's 0. All right. That question's done. Let's go ahead. This one, again, is just set up. So notice that I have this in terms of x's, right? Y equals sine of x. So when we set this up, I'm going to be using the x values. This one's a little bit tricky, right? They give you both the x and the y values. So we have to know, right, we're using the x values here. So it's going to go from 0 to 2 pi. It'd be kind of silly, at least in this example, to try to use the y's, right? Because it just goes from 0 to 0. So that wouldn't make so much sense. Set up, right, 1 plus the derivative squared. The derivative of sine is cosine. And that's it. This in general would be kind of a quite difficult problem in order to actually solve out. It would take quite a bit of time. So this is just one that, again, you'll see a few of these in your WebWork homework and stuff where it's just set up, but you don't have to evaluate. So you can see that those ones are pretty nice, all things considered, right? Because you don't have to do too much with it. All right, last one. This is kind of a conceptual one, so I do, I think it'd be kind of a jerk move to not go over it with you. But okay, which of the following values best approximates this integral? And so there's a couple things going on here. First of all, let's imagine we're on the final exam, right? Nothing about this question says anything about arc length. It says, here's an integral, right? Which of it best approximates? So, right, our goal is not to actually evaluate this out, and it'd be quite horrible, and might even be impossible to actually do this one out by hand without some sort of computer software. So, all right, our goal is not to do this. Our goal is to recognize that this looks a lot like the arc length equation, right? That we see stuff inside of a square root. We see the 1 plus a derivative squared. So this is arc length for, well, which equation? Well, it's the thing that you're taking the derivative of, right? And so notice that it didn't even evaluate this out. So it's the derivative of this equation, 5 over x squared plus 1. So it's the arc length for this function, y equals 5 over x squared plus 1. And notice we're on the interval from 0 to 2. So as x ranges from 0 to 2. So let me draw maybe a quick little picture to go along with this, and we'll approximate the arc length. Right, so if I was to plug in 0 into this, right, and I just want to know roughly where is it, well, if I plugged in 0 for x, right, we'd get out a height of y equals 5. 1, 2, 3, 4, 5. So we're up here at height 5 when I plug in x equals 0. If I was to plug in x equals 2, so I'm just looking at the endpoints, right, because we're approximating arc length here. So if I was to plug in x equals 2 into this, so we'd be over here at x equals 2. And let's see, we would have, again, there's just the x in the denominator here. So this is going to be 2 squared. That's going to be 4 plus 1. That's 5. Ah, that's very nice, right? So 5 divided by 5, that's just going to be 1. So we have down here at a height of 1. And again, this isn't going to be kind of a straight line or anything like this. It's going to have some curvature to it, right? It's going to kind of, you know, maybe it's interesting. But if we just want an approximation, right, at least a good starting point would be, well, how long is kind of the direct line going from this point to this point, right? So for instance, right now, I can already tell you from this, right, that D is completely unreasonable. Once we've said that this is arc length can't be negative, right? And in fact, we kind of see this, right, it's inside of a square root. Square roots only output positive values. So that one's gone, right? When I'm looking at this and I say, okay, well, I know that this is underestimated, but is there any way that this is close to 25? Now, that's going to be hard, right? Because again, we're going to use sort of the Pythagorean theorem here. This is going to be 2 over and 4 down, right? So the length of at least the direct line going to this is going to be the square root of 2 squared is going to be 4. 4 squared is going to be 16. So this is going to be around the square root of 20, a little bit longer than the square root of 20. Well, if it's longer than the square root of 20, there's no way that C is possible, right? Because again, this was the direct line going from one to the other. We know that our actual function is going to have a little bit of curvature to it, right? It's not going to be just a straight line. And likewise, 3 is not reasonable, right? Because 3 is also too small. I know it's bigger than the square root of 20. And so we have the options between 5 and 25 remaining. And so the square root of 25 would be 5. That's a little bit bigger than the square root of 20. 25 seems way out there. I mean, that would have to be a huge, you know, wiggly curve or something like this. And so the correct answer is going to be 5, right? 5, there's not that much kind of craziness to this function. It's going to be pretty close to a straight line, but it is a little bit longer than that. So yes, the 5 will be the best approximation for this. So again, this was a fairly conceptual one, right? But it all hinged on recognizing that this definite integral represents the length of the curve, right? If you were to actually try to take the derivative, square it, add the 1, take the square root, right? Again, I don't think this is possible without using some computer software in order to actually do this. Okay, I know we're 5 minutes over. We'll stick around for another couple minutes if there are any one-on-one questions or things that you'd like to ask about. Otherwise, thanks so much for joining, and we'll see you in Wednesday's class. We're going to be talking about 10.2 arc length for parametrized curves. And I'm going to stop the video there.